I'm from TRIUMF. TRIUMF is an accelerator lab at UBC. And we're currently, TRIUMF is working on several major projects, which means us small experiments have very little access to experts. So in order to combat that, we decided to, rather than having custom electronics developed, to try and see how far we can get with consumer grade electronics. The motivation for this is antimatter physics. So according to the standard model of particle physics, matter and antimatter should behave identically. This is something that the Alpha collaboration that I'm a part of has tested multiple times at CERN with trapped antihydrogen atoms. So in order to trap this antihydrogen, the procedure is we receive cold antiprotons from the antiproton decelerator and then combine them with positrons from a radioactive source and trap them in a magnetic minimum trap. Now, CERN is the only source of cold antiprotons in the world, so it's a very precious resource. So it doesn't really make sense to use it for developing trapping techniques and things like that. But because antimatter and matter behave the same way, why don't we just use hydrogen to develop the trapping rather than antihydrogen? That's where HAICU comes in. HAICU stands for Hydrogen Antihydrogen Infrastructure at Canadian Universities. And what we do there is we produce atomic hydrogen from hydrogen gas, decelerate it to a trappable energy, and then inject it into our magnetic minimum trap. So the way a magnetic minimum trap works is any atom with an unpaired electron has a magnetic moment, which means it's trappable in a magnetic minimum trap. So that means it's a magnetic field that grows in amplitude in all directions away from the center. Because this is a development platform, we decided to avoid going with the superconducting magnets we use at Alpha and instead go with conventional copper magnets. They're somewhat conventional, but they are bitter style magnets, which is, they look like what's shown there. The procedure is sometime when we're ready to trap antihydrogen, we energize the quadrupole. So that's the outside magnets that provide the radial confinement, and we energize the top. Is there a, oh, there, okay. The top coil here. And then we create the atomic hydrogen and bring it through the decelerator into the trap. And then by the time the hydrogen bounces off the top and makes it back to the bottom coil, we have to energize the bottom coil to its full current of 400 amps. Now the numbers are actually reasonably moderate, reasonably manageable. The hydrogen atoms travel at about 20 meters per second, which means it takes 10 milliseconds to travel through the trap and back. So that's the time we have to ramp this magnet up. I mean, that's still not a small feat, right? Going from 0 to 400 amps in 10 milliseconds is not nothing. But we don't actually care for about the timing to too much accuracy. So just for tunability, we want this to be reproducible to within 100 microseconds, which I imagine for most people here is basically whenever. So the power supplies we use are for the less time critical coils, we use these Sorensen power supplies that can be controlled with Skippy or with 0 to 10 volts analog. And for the fast bottom coil, we use this A-Tecron, which is an amplifier that will translate the 0 to 10 volt input voltage into, at the end, 0 to 400 amps current. So as I said, we want to go with consumer electronics. So this is based on a Raspberry Pi platform. The nice thing about a Raspberry Pi is you can get fully assembled hats that plug in, right? You don't have to build a custom board to get ADCs and DACs and all that kind of stuff. So this hat carries 8 24-bit ADC channels and 2 16-bit DAC channels, with both of them with a range of 0 to 5 volts. Now, as I mentioned before, the power supply is actually 0 to 10 volts. So we decided, for simplicity, to go with a separate hat for the DAC. So we're just using the ADC from this guy and the DAC from this guy, because then we can directly go to the 0 to 10 volt range. In order to control all the magnets, we need to control 4 Raspberry Pis, and they all have to be synchronized together. This is just done with an external trigger signal on one of the GPIO pins. So the idea is you load whatever ramp you want at your leisure, and then the Raspberry Pi just waits and fires that ramp whenever it gets its trigger signal. This is what the box looks like. So there's the 4 Raspberry Pis, Ethernet switch, and the connections to the power supplies back here. Now, this is my justification slide why this is at a sensors conference. This is the only slide that really has anything to do with measuring. So this setup needs to monitor both the monitoring outputs from the power supplies. So that is a 0 to 10 volt analog output that reports back the current and the voltage, as well as the 0 to 500 milliamp from the DCCT coils. So these are direct current transformers that we put on the magnet leads to accurately measure the current in the magnet. Both of those need to be read regularly, but during normal operation, once a second or something like that is fine, because there's nothing really happening there. That means that's also kind of the time scale that we need for PID control. So it's nothing, right? Timing doesn't enter into it. During ramps, we need to read them out much faster during the 10 millisecond ramp and stuff like that. But we're not actively reacting to this. We're just logging. So again, the timing is not as crucial, because you can just record what time you actually recorded it and fit it. So in order to figure out how these perform in terms of timing, this is kind of the test procedure. So the power supply itself is an analog device that doesn't introduce any jitter on that time scale. So the Raspberry Pis I've just set up to, when the trigger comes in, output a high signal on one of the GPIO pins and step the DAC to an arbitrary voltage. We then just put the trigger signal and these 2 signals in an oscilloscope and measure the delay times. Now, the main reason for jitter, presumably, is that the Raspberry Pi runs a regular Linux operating system, so it can just decide that the CPU has better things to do. So in order to figure out how much of an effect that is, we ran it with the regular idle operating system and with a CPU stressing program to just start extra processes. Because we have 4 Raspberry Pis in the box, we can have them in different configurations to test multiple things at the same time. The main settings we change is the thread that waits for the trigger signal can be pinned to one specific CPU core. And then you can tell the operating system on boot that core is out of bounds for the operating system. So then that thread is just pinned to that. Finally, there's the CPU governor, which is something I hadn't thought of originally, but it'll come up when I talk about the results now. So this is just the delay from the trigger signal to the GPIO output. And this is green is the vanilla Raspberry Pi just out of the box. So you see we're getting a spread of 400 microseconds or so. That's more than we want. Then if we run the stress, if we dedicate the core, this gets much better. We're already kind of in the almost 100 microseconds range here. Now, I expected when we run the stress program, this would get worse again. In fact, it got better. It took me a minute to figure that out. The reason is that the Raspberry Pi, by default, will step down the CPU frequency whenever it's idle. So in order to, and with the stress program running, it's never idle, so that didn't happen. But knowing that, you can just use the so-called CPU governor settings to just tell it, just always run at maximum frequency. And that's what this is, and you see it's almost identical to the stressed one. So this is the first part of the delay. Now the final step is just the delay to the actual DAC output. So this is just the same histogram as before. So this is just the delay from the trigger to the GPIO output. This is the total delay from the trigger to the DAC output. And this is the difference between the two to get it, to analyze it better. And you notice here, there's something weird. There are certain, there's a certain sub population of events that reacts 140 microseconds faster. Presumably that's something to do with I2C communication. I'm a physicist, I have no idea. But since this is of the order of less than 3% of events, we've decided we don't really care right now to investigate this. So we can just focus on the right peak here, and the width of this now is less than plus minus 30 microseconds, so well within our specifications. So conclusions, the system should be able to work well enough for what we want to do. We're currently building the trap, so we're currently assembling the magnets and everything. And are planning to power them up in January, which is when we can actually work on the PID control and things like that. Can't really do that without the actual system. And that's all I have. Oops, where's my, oh, there.